Yeah, welcome to my stream. Today I want to start a little bit earlier because I don't have too much time. I have to be away at 8, which would be in half an hour. So let's start this task fast. Let's get over to our task. And just across today's task is called Factory. Just across the hall, you find a large factory. Fortunately, the elves here have plenty of time to decorate. Unfortunately, it's because the factory machines are all offline and none of the elves can figure out the initialization procedure. The elves do have the manual for the machines, but the section detailing the initialization procedure was eaten by a Shiba Inu. All the remains of the manual are some indicator light diagrams, button wiring schematics, and voltage requirement for each machine. Here we see an example of our input. The manual describes one machine per line. Each line contains a single indicator light diagram in square brackets. One or more button wiring schematics in parentheses, and voltage requirements in curly braces. To start a machine, its indicator lights must match those shown in the diagram where dot means off and hashtag means on. The machine has the number of indicator lights shown, but its indicator lights are all initially off. So an indicator light diagram like dot, hashtag, hashtag, dot means that the machine has 4 indicator lights which are initially off, and that the goal is to simultaneously configure the first light to be off, the second light to be on, the third to be on, and the fourth to be off. You can toggle the state indicator lights by pushing off any of the listed buttons. Each button lists which indicator lights it toggles, where 0 means button, where 0 means the first light, 1 means the second light, and so on. When you push a button, each listed indicator light either turns on, it was off, or turns off, it was on. You have to push each button an integer number of times. Yeah, there is no such thing as pressing 1/2 time, or nor can you push a button negative number of times. So a button wiring schematic like 034 means that each time you push that button, the first, fourth, and the fifth indicator light would all toggle between on and off. If the indicator lights are, pushing the button, which changes them to be off, 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 on, off instead. Because none of the machines are running, the voltage requirements are irrelevant and can be safely ignored. You can push each button as many times as you like. However, to save on time, you will need to determine the fewest total presses required to correctly configure all indicator lights for all machines in your list. There are a few ways to correctly configure the first machine. Here are the examples, how to do that. I think we can skip the rest. I think the task is relatively clear. We have the indicator lights first, what we have to achieve. Then we have the configurations or the button press results. And then we have the voltage, which we can ignore for now. And then we simply have to find out the fewest button presses required to correctly configure the indicator lights, and then add them for each line. And then we get a result for task A. So then let's hop over to the code, and let's start by processing our input. So the first thing we have to do is split by \n anyway. Those are our machines, and then we can map that, and each line, the first, we should probably make a struct for that, call it machine, and then we need a vec of boolean, which are the lights. And then we get a those are the buttons. That would be a vec of usize. And then we get, yeah, shortages, which is a vec of usize as well, I guess. No, I think those should be those should be nums. They are not necessarily negative, but they are not indices either, while the buttons are all indices. So then impl for machine. Yeah, we could say from line, and then we take our line and stir and return a self. And then we can simply say here machine from line, and that will map onto a machine. I'm just doing it so the compiler's happy for now. Ah, of course. To define what values we're actually setting here. Yeah, of course. And then we want to collect that into a vec machines. So now how do we do from line? Now we have a line here. So the first, we have to split on space, of course. So let's collect that. Those are the line contents. We should collect them here simply. And now the first of the contents is our indicator lights. We could say replace the actual value in the this is an option. Unwrap. I want to work with the string here. Replace, yeah, and then we replace this with nothing, and we replace, or we say remove if that is possible. Why not? Does it mutate the string? That doesn't make sense. No method removed found on reference. Yeah. Then let's use replace and replace again. So now we have removed the square brackets from left and right. And now we can simply say chars map, and then we can say match C, and if it's a dot, then we want false, and if it's a hashtag, we want true. And otherwise we want to panic, because that shouldn't be possible. So, and then these are our lights, or it's our light configuration. We can collect that here. use lights here, and then, yeah, the collection type should also be clear. Okay, then we go to the next. I think we can copy this here for the buttons almost. So URL buttons. So, but we don't go over the contents. We say skip one and take contents len -2 because we don't want the first and we don't want the last. And there's no but last. Okay. So now we have our iterator over those pairs inside here. And then we want to map those to the button. And now we have to do this or something similar to the button. But we want to replace this and this with nothing. Then those are not chars what we are getting, but those are positions. And then we can say 2-digit with base 10. We had that a few times, that's why no. And then we say collect, which should collect into this returns an option. Then we say unwrap, and then we say SU size. Perfect. Now it collects, and now this is a vector of U size, exactly what we wanted. And now we only need the joltages, and the joltages are probably more similar. They are a mix of those two. So we take this, and we want the last, and we unwrap, and we replace this, and we don't take the chars, but do we take the chars? Yes, exactly. Those are now only the numbers. And then again, we say, I don't know what it is, so let's call it D for now and say D2 digit on base 10. Those are the joltages. So we remove those, we map them onto chars. We cannot, yeah, we can map them on the chars, but that is not a good idea. We need to actually split on comma, and then say 2-digit as num. What's your problem? Your problem is that this is now a string still, so we don't need 2-digit, but we need parse, and we don't need the base, but we need the type. And then it's a collect, and your problem is a value of type. We need to unwrap here, of course. Yes. Okay. And now here I made a mistake. Exactly. I said here chars, but we don't need chars. We also need to split on comma here. And then we have strings here. And then we also need to say parse. And the type is usize here for us. So we can remove that. Exactly. And now we have our input. Perfect. So quick sip from my coffee. So now we have them all split off. So now comes the interesting part. we have to loop. Now, first we have to, for machine in machines, iter over our machines. And then we need to loop. And let's say the light states, or light state, is machine lights. And then let's map them all. Oh no, let's do that. We map all lights to false. And then we collect them again into a vec. And we definitely have to declare this as mutable, as we have to change it later. Yeah, this can be an underscore, that's fine. So now we have to do this while light state is not equal to machine dot light. And we don't need that here. So while that is the case, we have to increase mutations is 0 in the beginning. And let mute total mutations. I just call it mutations for how often we changed the light states. So this is the local mutations, and we have to add those to the total mutations in the end. Sometimes I hate the auto formatting. Yeah. Okay. So what do we have to do here? We have to try all of our buttons to mutate our current states. So we always start with the light state, and then for each of our buttons we mutate it. And so we get, let's say we have 3 button states, then after the first mutation we get 3 button states, then we get 9 button states, and then we get 27 button states, and so on. We always multiply by the button states because we are pressing the buttons again and again. We could, of course, that would probably make the most sense. We make a states hash map, and we remember all the states we already had, because then we don't repeat a state that was already there. We actually don't need to make this a hash map. We can simply say this is a hash set. But the main point, I accidentally quit it, sorry. Data is here. So the main point is we do not repeat. So let's say one of the buttons just switches a single state. Instead of pressing that button over and over and over again for our mutations, we simply do the changes once, and then we know we already did that, and we don't need to do that again. We don't need to press the button over and over again and store its results and then do mutations on it, because it's already an initial state we already had. I hope that makes sense. So the states, let's be mute. And the states start with our initial light state. And of course, can you be, no, you, sorry. This needs to be owned. So we have to clone here. Okay. Then I think we need 2 for loops now for each button in machine.buttons. We have to apply the button to each state for Thanks very much. I was so confused by that sound. For state in... Yeah, I'm fine. And you? Yeah, I'm currently doing advance of codes. Yeah, and I think the task's going well. Just finished part 2. It's pretty tough today. Yeah, I don't know. I'm sadly I don't have too much time today, so maybe I will continue in the evening. But in the morning I don't have too much time. But I thought yesterday was already pretty tough. I couldn't even finish part 2. Don't know about you, how that was going. But yeah, if today is as tough again, I think that's going to be pretty hard. Yeah, definitely. I'm glad there are only 12 days this year. If there were 24 and they were as hard as yesterday and then today, probably that's don't know if I could manage. Okay. Yeah, so we have our machine buttons and we iter over the buttons and then we iter over the states we currently have. Yeah, I also think the difficulty is probably raised faster. I mean, it's only today, tomorrow, and the day after that, so they gotta spike it up real fast. But I think it's last year. I remember that around day 10 it also got really hard, and that's when I stopped last time. But yeah, I think this year is next level. Okay, I'm not sure if here. Yeah. In which language did you do it? Are you also using Rust or using some other language? Yeah, I think Python is also a better idea because it's already so hard to start with parsing. Yeah, definitely. I'm also using Rust because it's I want to get better at it. I've used Python for quite some time, and I don't use it professionally, so there's no real use for it except for scripting. But yeah, Rust is really hard, and it takes much more time, I think, to even get started in Rust than doing it in Python. So now I think I have to clone the state here because I want to mutate it. So let's mute and then for in button iter state at pos is equal is equal to not stated pos. So we have, yeah, I think we need to dereference here. We clone the states, we mutate the state here, like the button dictates, and then we simply add that state again into our, not state, but the states. Let's insert the state here. And what is the problem? Cannot borrow states is mutable because it's also borrowed as immutable. So we cloned the state here, so we're using that, so probably the borrow happens inside the for loop. Immutable borrow. Okay, we are, yeah, we're iterating over the states, and that's why we can't insert something into the states while we are iterating over them, which of course makes sense. So let's make new states are equal to states copy clone. And then we can insert this into the new states. And then let's say states is equal to new states. And of course, the new states need to be mutable in this position. And now we have our new states. And that should be it, I think. Yeah, this is not correct. We don't have to check against this. While states iter any, not any, but all, while all are not equal to our machine lights. And then we can dereference that here. Yeah, that should be it. While none is equal to the state lights. No, wait. While all are not equal, so that should be it. Okay, so while all states we have are not equal to this, we simply go over the button, mutate all states, add them to the new states, and then we have our new states. And then we have to increase our mutations. And the light state is actually not necessary. We could... we could... do that here as well, but then we have to define the type. Yeah. Okay. Yeah, that should be it, I think. Let's maybe run the test. Okay, what's going on? We only get 3, even though we are supposed to get 7. Okay, so 3 is a little bit... Okay, then let's start with our trusty debugger. Looks all right to me, but okay, let's have a look. Okay, we start with our states. We add the states We have one state with false, 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 false. That is, of course, correct. And our machine lights. We cannot access them like this, but we can check here. Is false, true, true, false. Okay. Then we go over our buttons. I see the problem. We cannot do it like that, of course. Sorry. The problem is that we are changing the states when we iterate over the buttons. That is, of course, not what we can do. That is not alright. We have to take the new states. The new states can only be applied after we have iterated once. Yeah, so we take our new states, we iterate over every state. And for each button, we clone the state, we apply the state to the button and add the state where the button was applied back to the new states, and then we set them, and then we increase the mutation. Otherwise we operate on the results too early and take new states too early. And this worked. So then let's run this. That will work. We have to use state 10. And let's run this, and we get an exception. Of course, we get an exception because I haven't pasted anything into the input yet. Then let me go over to the task real quick. Copy the input. And let's run this again. 455. Let's check back with AOC. And 455 is the correct answer. So then let's check out part 2. Thanks, man. I just saw the comment on the ASCII art. Yeah, I took some time to make a random generator that simply generates some ASCII art when this is run. That was fun. Yeah. Oh. Okay. Now we got part 1 done. And I guess part 2 is now the real hard part. And I guess I'm not going to finish it today, but I would, or at least not right now. I would look into it right now. And let's see. So part 2, all of the machines are starting to come online. Now it's time to worry about the joltage requirements. Each machine needs to be configured to exactly the specific joltage levels to function properly. Below the buttons on each machine is a big lever that you can use to switch the buttons from configuring the indicator lights to increasing the joltage levels. Ignore the indicator light diagrams. The machines each have a set of numeric counters tracking its joltage levels, 1 counter per joltage requirement. The counters are all initially set to 0. So joltage requirements like 3547 mean that the machine has 4 counters which are initially 0, and that the goal is to simultaneously configure the first counter to be 3, the second counter to be 5, the third to be 4, and the fourth to be 7. The button wiring schematics are still relevant. In this new joltage configuration mode, each button now indicates which counter it affects, where 0 means the first counter, 1 means the second counter, and so on. When you push a button, each listed counter is increased by 1. So a button wiring schematic like 1.3 means that each time you push that button, the second and fourth counters would each increase by 1. If the current voltage levels were 0, 1, 2, 3, pushing the button would change them to be 0, 2, 2, 4. You can push each button as many times as you like. However, your finger is getting sore from all button pushing, and so you will need to determine the fuse total presses required to correctly configure each machine's voltage level. Counters to match the specified voltage requirement. Consider again the example from before. Yeah, configuring the first machine counters requires a minimum of 10 button presses. Yeah, okay, I'm gonna skip the last part. I think I get the idea. Okay. Yeah, I think the main problem here is the that we get so many states, which would lead to a really huge runtime. If we keep pressing the buttons, the states are gonna explode. I mean, we have to at least press one button 7 times here. We probably have to press, and here even 12 times. So if we just keep pressing the states, there are going to be too many states we have to keep track of, which will take way too much time. So we definitely have to use a set to keep the states low and maybe rule out some cases we don't have to iterate on if they already violate one of the conditions. Yeah, but I see that's probably, yeah. Yeah, it's I did Advent of Code the I think it's the 3rd or 4th year I'm doing it, and at the beginning I was always the exploding states, and the runtime was always killing me. I still remember one time back, I think 3 years ago, and I was or even 4 or 5 years ago, and I was using Java, and I was creating an object for like super exploding states, and like my entire computer was almost freezing because of the exploding states, and I was trying to create so many objects, and at some point the virtual machine just crashed because I got an out of memory exception. And yeah. Since then I always worry about the states here in Advent of Code. Okay, but it's 8 and I have to get ready for work. I had that too in the past. My program started using so much memory and swapped that my entire computer froze. Once that was just for fun. There was one task where I had a brute force solution that worked, but it took some time, and I then parallelized the solution and just used as many threads that I could use. And my entire computer was like, I looked at HTOP, and my entire computer, all my cores were at 100%, and yeah, you can really stress out your computer with some solutions here. Yeah, but what I wanted to say is it's 8 o'clock, and I'm going to call it a day here. And yeah, maybe I will come on again in the evening. No, I can't do it today. Yeah, so I have to finish this up tomorrow probably. I will probably do it tomorrow after the first after day 11. If day 11 is doable and I have some more time left, I will do it tomorrow. Otherwise I will find some time to do it. Thanks for being here, Vasha. You're the first person I do not know which participated in the stream here. And yeah, was really nice talking to you. So yeah, then I would say. Hopefully see you tomorrow, otherwise maybe some other time. And yeah, bye bye.